Welcome. Let us consider the solutions of a homogeneous matrix equation A times x equals 0. You know that this equation always has the trivial solution, x equals 0. And depending on the number of free variables you obtain when row reducing the matrix A, the set of solutions is either just a single point, a line, a plane, etc. For the matrix on the slide, it is the indicated plane. An important property of sets of solutions to homogeneous equations is the concept of superposition. If you take a multiple of a solution, you obtain a new solution. For example, twice the yellow vector is another solution. Moreover, if you have two solutions, the two yellow vectors on the slide, then the orange sum of the two solutions is another solution. You already used superposition in the context of second-order linear differential equations to go from a few specific solutions, for example e to the x and e to the 2x, to the general solution y equals c1 e to the x plus c2 e to the 2x of the homogeneous equation. This superposition property severely restricts what the set of solutions to a homogeneous equation may look like. Indeed, consider the disk around the origin in the picture. Can this be the solution set of a homogeneous equation? Nope. The sum of the two indicated vectors is not in the disk. What about everything to the right of the y-axis? Nope. -1 times the indicated vector is not in this set. Indeed, the only possible sets satisfying the superposition principle are basically the lines, planes, etc. passing through the origin. A linear subspace of Rn is a set which satisfies the superposition principle. So it contains the origin, the trivial solution, sums of vectors in this set give a new vector in this set, and multiples of vectors are also contained in this set. At the bottom of the slide, you can see some examples of subspaces of R3. Another subspace of R3 is R3 itself, but that's rather hard to draw. Linear subspaces arise in several different ways in linear algebra. You've already seen that the null space of a matrix, the set of solutions to the equation A times x equals 0, is a linear subspace. For the given matrix A, you can easily calculate that it is a plane through the origin. Note that we see this by rewriting the null space as all linear combinations of the two vectors -2, 1, 0 and -3, 0, 2. This gives another example. The set of all linear combinations of a set of vectors, their span, satisfies the superposition principle as well, and is therefore a linear subspace itself. If the vectors v1, v2, etc. are in a subspace, then multiples and sums of multiples must also be in that subspace, due to the superposition principle. So all linear combinations of these vectors must also be in the subspace. The span is the smallest set of vectors you can have, which includes v1, v2, etc., and which still is a subspace. Another important example is the column space of the matrix A. This is the set of all vectors which can be written as A times x for some vector x. It is called the column space because it's the span of all the columns of the matrix A. Indeed, you know that by definition of the matrix vector product, that A times x is x1 times the first column of A plus x2 times the second column, etc. So different vectors x create all linear combinations of the columns as outcomes of A times x. In this case, all columns are multiples of the vector 1, 2. So the outcomes are all multiples of 1, 2 as well. These vectors form the column space of A, a line through the origin in R2. Because you can add and multiply vectors within a subspace, you can calculate within this subspace just as you can in an Rn. In this way, you can view a subspace as a set that behaves like an Rn inside an Rm for some bigger m. For example, you can add and multiply vectors on a line through the origin, just as you can add and multiply numbers on the real line R. And you can calculate with the vectors in a plane through the origin as if it was R2. You can make this connection between a subspace and calculating in Rn precise using the concept of bases. You will learn about bases in class. See you there.